I haven't really looked at it, but we're doing something in Desmos to introduce the concept.
For tomorrow?
Mm-hmm.
Oh, so I'm not now.
There's 2 problems I think you have to do. Hi.
Today we have 2 problems.
Tomorrow we will. Basically, the last section is all about the different kinds of exponential models that we could actually have. So we're going over exponential growth and decay, even though we should technically know these already because we graphed these in section 1. Then there's the logistic model tomorrow, and then there's like a logarithmic model. And Friday, maybe there's one more with that. So basically, we create models to represent data, so that way we can make predictions about all sorts of things. So, here we go. Does anybody remember what we know about exponential growth models and exponential decay models? What does it look like? What's the equations? What's happening? Okay, exponential growth, we are increasing. So, graphically speaking, it should look like this. Does anybody remember what the model looks like? The equation for it? Okay. There was a kid that represented like the root class or the horizontal asymptote.
X minus H squared plus K. Is it that or is it no?
That's a quadratic.
Okay.
A.
Okay, so exponential, we're going to have an exponent, definitely, since that's in the name of it. We could have any kind of base. We're going to work specifically with a base of e. And then we could have, I think they use a bx. I don't know if you use the letter b, but we're going to. And then we have like plus k. Right? So the k value of this is the horizontal asymptote. If it's growth, then we know b should be positive. So that way we are rising instead of falling. Same thing with a. A has to be greater than 0. That means it's above the x-axis. If it's less than 0, then it's below the x-axis. Yeah. So sometimes this k value you don't necessarily need. So depending on what the problem is representing, should the horizontal asymptote be on the x-axis or should it be up or down a little bit? Yeah. So you have to make that judgment call basically, if you need it. Okay, so then we have exponential decay. So we should know this is falling. Growth is rising, decay is falling. And the model is basically the exact same thing. I'm going to put a negative into it. So that way my exponent is negative, that's telling me it's a decay model. But everything else is the same thing. So A has to be positive for it to be above the x-axis. A is less than 0 than it's below. K is still the horizontal asymptote. So we basically force B to be negative to represent a decay model. Okay. We have, I think, 3 problems. Did we get that up there? Okay, So create a table for the time t necessary for key dollars to triple if interest is compounded continuously at a rate r. When r is 2%, 4%, 6%, 15%, 10%, 4%. Using Desmos create a scatter plot of the data and find a model that fits the data. So we're going to use PERT. Okay. Ooh, I was confused. Now I think I understand what we're doing. Right, because there's not a lot of information here with what we're getting. Okay. So this is what we're going to do. We're going to create a table with R and T. So R we know is 0.02, 0.04, 6, 8, 10, and 12. So then we're going to find the time necessary to triple the amount. So technically we don't even need to know the principal amounts if I know we're tripling. I got it. Yep. Okay. So we're using this tripling thing. So I can have P to represent whatever dollar amount, basically. Right, so that's my starting value. My A is going to be 3 times P. Right, so if the principal is $1,000, I know I want my amount to be $3,000 to triple it. Okay, so I can plug in 3P in for A, since I know I want to triple it. And then the p's cancel on both sides, so this is the equation we're going to work with to find the time necessary with each interest rate. Everybody with me? Okay. So plugging in 0.02, we have 3 equals p to 0.02t. And I would like to solve this for time.
Do I put E for the 0.02 and then she'll take the
Natural on both sides. Cancel the e out. So the on the right side is 0.02. The left side, whatever natural log of 3 is. Good enough. So then divide by 0.02. So then 2 is approximately. Okay. So we have to do that with all the rest of these. So speed up the process. Riley's going to do 4%. Chloe's going to do 6%. Allie's going to do 8%. Trey's 10%. Tyson's 6%. Okay. 24. We're basically solving this equation, but 0.02 is GP for whatever percentage that you're doing.
Oh,
I got 18.3.
Okay.
13.7.
yeah, 9.2.
Alright, Trey, you should be between 13.7 and 9.2.
Oh. Wait, what? E to the 1.
What are you doing?
Well, I use for all.
Yeah. That's what you're solving? So you're good in natural on both sides?
Oh, I saw it for T. I plugged it into
Whew! Trey's gonna get there.
the second slow. 10.986.
Yay. Okay, so there's our table. So we're gonna use Desmos to create a scatter plot and find a model that fits the data. So, if you remember how to use Desmos.
Isn't there a thing we can choose to type in values in the table?
Yep. Yeah, so if you go to desmos.com, there's like a big red button that says start graphing. You're gonna click that. So to insert a table into Desmos, there's this plus sign in the top left corner if you're in the graphing feature. So you press the plus sign and go to table, and then you just can enter all this data into that table. So you have x1, y1,
What do you think it is?
the plus sign in the left corner. So yeah, press graphing calculator first. Yeah, it should be plotted for you to like zoom out or in. There's like a wrench in the right corner that you can adjust the x-axis if you don't want to zoom it out. Okay. So yeah, the points should all be plotted. You might have to adjust it. It should look like they are an exponential decay. So not a straight line, but like curved slightly. That depends if you're zoomed in or out. Far enough.
Mine is very straight.
So yours looks really weird. I would go to the wrench. And then your x-axis from like -1 to 1. Your x-axis. Great. That looks a little better at least. Okay. So see your data should look like exponential decay if you're in the right window. Anyways. But line 2 we want to type our model. So we know it's going to be exponential decay. So we do have our like standard format for exponential decay, which we said before that it was like y equals a e to the negative x power plus k. Yeah. So even here I probably wouldn't even put enough horizontal asymptote. Because asymptote would probably just approach the x-axis. So you want to type this in, but you need to make a few adjustments. Like your table is in terms of x1, y1. So when you do this, you need to have y1 and x1 when you type in the model. And then the equal sign is changed out for this little squiggly. So that's like coding that's supposed to be what you want it to do. And then it'll give you the value of a and the value of b. That's in the second line, that's what you have to type. Or you press the plus sign and do an expression. The top left corner of the keyboard. We have to do a subscript for y and a subscript for x.
You have to put Y1 on the.
Yep. That's
How do you do subscript?
like you shift and the minus sign.
That won't go big.
You have to figure out it. So
And
the
then
line.
with this
Well,
one,
no, you shift and then the minus sign. Oh, that's fine. And then you can make the right line.
How do you
Make it go
go
to
to
the
the
top
top?
of the window there.
How do you get it to the top?
Shift and the plus sign. Oh. Well, yours is different. Oh no, you shift and then this one. Yeah. There it is. Okay. Shift and six. Control. Well, it should generate the value of A and the value of B. Which it did. So then that's our model. Take down y equals like 83.6 e negative 23.6 x power. So this is what Riley's gave her. It should be the same for everybody. You should have a 6 there.
Oh, it's because I'm trying to the top thing.
So this is weird. Why does it not work? Weird. I mean, yours are almost the same. Yeah, so since you put in a horizontal axis, it feels slightly. We didn't do the horizontal axis.
So I did have to bring that in.
Okay.
Wait. That. I'm not.
You got it?
Don't. Yeah. I said don't.
Okay. Did anybody see what their R squared value was?
0.95.
Does anybody know what that means? We talk about it briefly, like every time we do this. So R is like the correlation coefficient, so that's telling you the strength of your model. So basically, the closer it is to 1, the greater the percentage that this model fits the data. Right? So we're saying it's basically like 95% accurate. It's kind of what that means. Okay? So most of the time, Desmos, if we're doing this, it's going to be in the 0.9s. So we're going to do more Desmos. I think after we finish this chapter, there's like a project we're going to do. So we're going to have to remember how to code our computer to do this for us. It's going to be great fun. Okay. No more. So the population P of the city is given by P equals that lovely thing. No. That was one thing we were going to do with that. So we have T equals 0 represents 1996. According to this model, when did the population reach? 150,000. Okay, so our model looks like this. Put that on my computer stuff. So this one we should know how to do since we've been solving exponentials for a while. What would be a fun project is analyzing the data of COVID cases. Would that be interesting? Okay. Anybody know what we're doing here?
Trying to find T.
Okay. So what is P?
150,000.
So we're going to plug in 150,000 and then solve this equation for P. Yes. So what are we doing first?
Right. Now, I think.
Did you get that decimal string?
1.574.
Okay. And then what do we need to do? Yeah. So Larry, say natural log and cancel. I have no idea what natural log is. I'm thinking that's important.
.454.
Okay. So then dividing.
8.248 years.
So then what year would that be? So I think our starting year was 1996? Four. 1996? 2004? Not too shabby, it's just like sort of problem. But what we've been doing this whole time? This one is the fun one. What? Basically, it's when we're using exponential growth. This one gives you the data. Population of fruit flies. How interesting. Yeah, if they didn't tell you it was exponential growth, you could basically find a model for any of it. So you can do a linear model, a quadratic model, a rational model, a linear model. So if you don't know if it's exponential, then this is just kind of, Okay, what's our model for exponential growth again? Yeah, and I'm going to ignore the plus k. Typically, we're just going to use this guy without k. Okay. So, what does this whole 2 days and 125 flies and 4 days and 350 flies represent? Any guesses? So I always think time is the x value. So 2 days is representing x, 4 days is representing x. So 2 days goes with 125, so I have to write them together. So this is going to be my y value. So I have an ordered pair of 2, 125. And then the second ordered pair of 4, 350. So since these go hand in hand, we have to write them. So basically, I'm trying to figure out 6, something. So if this was linear, we would just subtract the y values and add it to 350. That'd be easy. Exponential growth doesn't necessarily work like that. So we have to figure out what are the a and b values of my model using these 4 pairs. So we're going to plug in 2, 125 into my model and 4, 350 into my model. So my first equation I have is 125 equals a b, the b times 2 power. And I could do it again with 4 and 350. So I have 350 equals a b to b times 4 power. 980 is this to find the value of a and the value of b. So basically, we have a system of equations. I have 2 equations with 2 variables. Following a system, we can use substitution method or elimination method. Any preferences? Substitution method. Okay, does anybody know how to use the substitution method? We've heard of substitution method, correct? Okay. So basically, it's telling you exactly what you need to do. You need to substitute whatever expression into the other one. So we basically want to combine these two equations together, but to do that, I should solve either expression for A or B. So what do you want to solve for? Which one would be easier, solving for A or solving for B? Okay. So I'm just going to do the first equation. How would I get A by itself?
Subtracting 2 from the left side and then divide it out.
Yeah, I would divide. You know, like 125 over on the left side. Yeah. A is being multiplied to E. So we're just going to divide E both sides. What's its exponent? So basically, A is equal to this. So now we can use this and substitute it into the other one. So this expression is going right there. This is where we're combining the two equations together, so that way we can solve for one variable. Okay. So this equation, I now need to solve it for B. So I would like to combine e to the 4b power and e to the 2b power. Okay, so I want to combine the exponents, but they're not like being multiplied together, like in the numerator. Like one's in the numerator, one's in the denominator. So we're going to do something different. Yeah. So Riley wants to flip it, so that way my e's are in the same spot. So we have 125 over e to the 2b, and 1 over e to the 4, negative 4b. This is one way to do it. There's many different ways to do this. So now you can combine the exponents by adding them, since they're both in the denominator. Okay, so now it's going to be, which is nice. Where would you like to go from here? Mm, okay. Multiply by what's in the denominator. Now let okay. Oh, Okay, so we found the B value, but we still need to find the A value. Right, so going back up to this guy, gonna substitute it in. So it's 5 and 5. Yeah. That's the whole answer. I don't know if that was just the denominator of the whole thing. Okay, so our goal was to write our model, so that way we can evaluate at 6 days. Remember our model we started with a the bx power, so now we can replace the a value with 44.626, and the b value is 0.595. And we wanted to find the population fruit flies at 6 days. So since we have our model, we can just substitute 6 in for x. So we have this many fruit flies after 6 days. It's a lot of fruit flies. Super fun. Woo! 3 minutes before the bell even. Crushed it.
Just getting your sign.
But if you do this class time tomorrow, your topic.
Maybe later.